That you want to ask question towards the end, either on the chat or by raising your hand. So Henry, please go ahead.
Thanks for the introduction, and I'm sure we would all prefer to be enjoying our time in Cape Town, enjoying our first strings on the African continent, but I think great credit has to go to the organizers for bringing this online and to such a wide audience, and also thanks for giving me the opportunity to present this work based on this paper that just came out a week or so ago, and I should also highlight independent work that at least in these JT gravity aspects is very closely related. It's independent work by Witten that also came out last week. So this is the most important slide, which is to highlight my collaborator, Joaquin, who is also a postdoc at UCSB, and none of this, what I'm presenting you today, would have been possible without his hard work and input. So make sure he gets the credit he deserves. Okay, so the sort of overall philosophy that's motivating this is a lesson that's come from the last few years, which is that semi-classical gravity, and really just a semi-classical low energy theory, not necessarily worrying about strings or so forth, can actually tell us a lot more than we might have expected. So I think we'll hear a lot about the page curve later this week from semi-classical physics, and other things about, for example, fine-grained hallmarks of discrete spectrum in quantum mechanics and quantum chaos and so forth. Things that we really wouldn't necessarily have expected from a semi-classical theory are nonetheless there. So this really motivates us to just understand just a path integral over metrics, say, as a low energy theory. So I'm going to talk today about two very simple kind of case studies in this. So the first one is 3D pure gravity in ADS, which is an old subject of study. And to begin with, the story is a little bit pessimistic. So recently it was sort of conjectured that perhaps this theory doesn't exist or is not consistent. So the story, as far as I'm concerned, goes back to this work of Maloney and Witten, who took a very natural approach to understand the spectrum of pure 3D gravity. So they constructed the partition function and performed the path integral by looking at all the classical solutions with the relevant boundary conditions, computing their actions, computing all the loop corrections, and doing the complete sum over saddle points. And this is a very natural way to construct a partition function. But there's a sort of serious problem with this that was pointed out a year or so ago by these authors, which is that this resulting spectrum that was also studied by Keller and Maloney actually has a negative density of states in a particular region, and that region is very, very low temperature rotating BTC black holes. And there were some suggestions on how to propose this. So one recent work of Benjamin Collier Maloney, for example. But these all amounted to adding some matter and changing the dynamics of the theory. The first aim of today is to actually propose a solution that's of how you go beyond this Maloney-Witten type analysis and to solve this problem with a negative density of states just within gravity itself with metric degrees of freedom. The second thing I'm going to talk about, which turns out to be very closely related, is about 2D JT gravity. And it was a beautiful paper of Stajchenko and Stanford, which I think was talked about at Strings last year by Steve Schenker, and very closely related work by Stanford and Witten. They were able, this is a sort of the very simplest theory of gravity in some sense. It's two-dimensional theory, and the path integral there you could actually perform exactly. And the new ingredient that will be importing to 3D gravity is this feature, the topologies included in this path integral included topologies where there's no classical solutions. So that goes beyond this Maloney-Witten proposal for 3D gravity. And the other really amazing feature of this was there was a new notion of sort of ADS-CFT duality. We're used to the idea of having a dual quantum mechanics with some definite spectrum and Hamiltonian and so forth, like Rajesh was telling us about just in the last hour, that here there's something very different, where there's not a definite Hamiltonian, but rather a probability distribution, and a very special type of probability distribution, a matrix integral. So we're going to talk about that. So the second main aim of this talk is to generalize this correspondence between JT gravity and matrix integrals. And these two things will turn out to be very closely related, and makes us speculate that perhaps this funny feature of JT gravity, that it has this ensemble dual, maybe also the case in 3D gravity, but that's more speculative. Okay, so let's start off with a bit of motivation from pure 3D gravity. So the first thing I'm going to do is relate this to a two-dimensional problem, which some hint of why these things are related. So we're going to start with, this is the usual Einstein-Hilbert action with a negative cosmological constant. And you can reduce this to two-dimensional JT gravity, and this is very indicative of how JT appears as a sector of higher dimensional models for near extremal black holes. You do the usual sort of KK reduction, you get this dilaton field that tells you about the size of a circle, and this Kluser-Klein gauge field. And so this was a dilaton, Einstein-Maxwell dilaton action written down sort of 25 years ago. It turns out to be convenient to actually work in a different ensemble, fix the angular momentum, rather than, so the usual boundary conditions here would correspond in an ADS3, the usual boundary conditions would correspond to fixed holonomy for this gauge field, which is the same thing as a fixed chemical potential for the angular momentum. But here we're going to work in an ensemble with fixed J. It turns out you can integrate out the gauge field, it's got a local effective action, and you just end up with a Maxwell-Dilaton theory. And then you can look at a near horizon limit of a near extremal black hole, where the dilaton is almost some constant value plus some small fluctuations. So this chi term here, this is the Euler characteristic, which is just the Einstein-Hilbert action in 2 dimensions, which is topological. And so this is, because you're essentially trivial physics, it only tells you about the ground state. If you want to be able to go to finite temperature, you need to include some extra small deviations. And that's what JT gravity does for you. Okay. And in this paper with Anami Ghosh and Joaquin in December, we actually showed that this ADS2 physics is really there in very generic 2-dimensional CFTs, which you can show using a conformal bootstrap. So this 2-dimensional theory is a very good description of the physics that goes on at very low temperature for large rotating BTC black holes. Good. Okay, so now we should have a look at where this negative density of states I talked about comes from. So we want to compute the partition function. We're computing the path integral, therefore, with some torus boundary with a spatial circle labeled by phi and some Euclidean time circle. And to get do the path integral, we need to find 3-dimensional geometries with this torus as a boundary. So for that, we need to choose some cycle of this torus to fill in. So the simplest case here is the ADS, just you fill in the spatial cycle. This gives you just the empty ADS3, which describes the vacuum state. That's not so interesting for us. Another thing you is fill in the Euclidean time circle. And as usual, this gives you a black hole, gives you the BTZ black hole. And if you go very near extremality for this solution, the corresponding density of states looks like this. So E equals J corresponds to an extremal rotating BTZ black hole. If you go slightly away, there's this square root edge in the spectrum, and it's multiplied by a very large number. S0 is this Bekenstein-Hawking entry of the black hole, the extremal black hole. But there's no problem here. In fact, we can reduce, just throw away this spatial circle, and we just left with a disk. So you end up with a hyperbolic disk in the near horizon. There's a circle fibered over ADS2. And this is where the JT gravity comes in, that we were talking about before. But there's no problem with negative density of states here. So we have to include another solution to see that. And that comes from the so-called SL2Z black holes. It's a family of these black holes where we fill in a different cycle. So the most important one is the one I've drawn here, where this the cycle we're filling in actually wraps twice around the Euclidean time circle while it goes once around the spatial circle. These generalized, but this is the most important one. And this gives a contribution that looks like this. So it grows much slower with the Bekenstein-Hawking entropy, so it's usually much smaller. We don't have to worry about it. But very close to extremality, it's enhanced by this this sort of square root singularity instead. And it's also got this sign that depends on the spin. And as pointed out by these authors, if you go very, very close to extremality, is an exponentially low temperature, this second term beats the first term. And the overall thing is negative for odd spins. So this is the problem. This is where the original problem comes from when you have to work out some solution. Okay, but we've already motivated that ADS2 physics, two-dimensional physics, is a good way to describe the problem. So let's see what happens to these SL2Z black holes when we throw away this spatial circle and try to describe it in terms of 2 dimensions. What we discover is that the two-dimensional geometry is actually singular. So the fact that this cycle, the time circle twice, the result of that in 2 dimensions is you end up with this pi conical defect somewhere in this 2-dimensional. And there's also a singular, there's a Kaluza, and that Kaluza-Klein gauge field has some singular holonomy as you go around this defect. And this, and these two things actually conspire to make the solution smooth in 3 dimensions while it's singular in 2 dimensions. Roughly speaking, what happens is as you go around this defect, you actually also, at the same time, go halfway around this spatial circle. And you have to go twice around the defect to come all the way around the spatial circle and back to where you started. So that's why it's smooth. Okay, so this motivates us to upgrade our Jaqueff-Teitelbaum gravity theory we were talking about before, that gives us the physics of just the BTZ black hole, and we should include things that describe these sorts of defects. Okay, so that's sort of motivation. So yeah, maybe I'll just give this a name so I can refer to it later. We'll call this defect a Kaluza-Klein instanton, in analogy with the Kaluza-Klein monopoles that you get, say a Dirac monopole in 4 dimensions that you get from dimensional reduction of smooth solutions in 5-dimensional Einstein gravity. Okay, so that brings us to the next section of the talk. So we were motivated to include these defects in JT gravity, but we're not necessarily limited to this scope of 3-dimensional gravity. So what I'm going to do is just study these as a theory in their own right. We're going to just augment JT gravity with these new objects that produce these singularities and see what it looks like. Okay, so the first thing I'll have to do is give a quick review of the paper of Sadchenko and Stanford, where they solve JT gravity, because we'll be really following quite closely their approach here. So first of all, what does the theory look like? Here's your action, which is the same thing I wrote before, now with the boundary term. Got this topological term we mentioned before. And the boundary conditions here are that we're going to take some constant but very large value of this dilaton field phi, and that's also going to have a very large proper length. So this is taking the boundary to be large and far away, but we're going to hold the ratio between these two things fixed. And this is actually the ordinary sort of boundary conditions we would use in ADS-CFT, but just adapted to this particular case. And this path integral is going to have n of these asymptotic boundaries. And this left-hand side so far is just notation for the path integral with n asymptotes. And the fact that we're talking about disconnected Euclidean boundaries is a signature that there's going to be something interesting about this theory, and where this ensemble interpretation ultimately comes from. But for now, it's just going to be denoting the boundary conditions of the path integral. Okay, so first of all, we can start with the classical solutions. The key to solving this theory is the way that phi, the dilaton phi, appears into action. It just appears linearly, which means it's just a Lagrange multiplier. So once we integrate it out, we are restricting to the slice where this curvature is negative. So that means that we're locally next to space. There's one classical solution to this theory, which is the hyperbolic disk, the thing that corresponded to the BTZ black hole before. And then there's some perturbative corrections here that come from the fact that the boundary doesn't just have to be a circle here, it can have some wiggly shape. And we have to integrate over all the possible shapes this can be. And the dynamics of that comes down to this boundary term here. And this becomes the famous Schwarzian action, which has been discussed by these authors in various different contexts. And it gives you some exact result for the density of states. And we should note in particular that the partition function or the density of states here are multiplied by this factor e to the S0. So this S0 is telling us a zero temperature entropy, roughly speaking, or the zero temperature classical entropy. Okay. Good, but now we can go beyond the disk and look at other topologies as well, because we've got this this fact that we're on constant curvature surfaces. The path integral, this infinite dimensional path integral, restricts to a finite dimensional integral over hyperbolic surfaces. It turns out that the appropriate measure you get is the very natural one here, is the Weil-Petersen measure. So roughly speaking, we can split the path integral into two pieces. One is the what's going on in the bulk, which is this finite dimensional integral over locally ADS2 metrics, and then this boundary integral, which is this Schwarzian mode mentioned before. So let's be a little bit more concrete about that. We can write the path integral with n boundaries. We'll just concentrate on the connected piece as a sum over topologies. Topologies in 2 dimensions are, of course, just classified by their genus. They're weighted by this topological term, and then there's some n boundary genus G amplitude. So this is what it looks like, and we're going to calculate it just by cutting it in 2. So you can cut it along a geodesic here, the sort of outermost geodesic for each boundary. It's just one boundary here, but you'd have one geodesic for every boundary. There's the piece outside, which I'll call the trumpet, which is bounded by a geodesic of length b here, and here you've got a Schwarzian mode, and this is this you can calculate. It was worked out by, again, Serge Stanford. Then you've got this interior piece where you integrate this finite dimensional integral over the moduli of this surface. This means you're just counting the number of hyperbolic surfaces, and you get the so-called Weil-Petersen volume of hyperbolic surfaces with boundaries of specified lengths b. And then you just have to glue these things together and finally integrate over this length b with the right measure, and you get this expression at the bottom for the path integral. Good, so that gives us everything we need to solve the path integral. So what do we get? The key piece we need to be able to understand to evaluate this are these volumes. How do we actually calculate these things? Well, fortunately, Marian Mirzakhani obtained a beautiful recursion relation for these volumes. And it was observed by Eynard and Orentin that this recursion relation of Mirzakhani is very closely related to something called topological recursion that appears in the theory of matrix integrals. So you should just briefly review what a matrix integral is, because again, that's going to be important for us. So here we're defining something that looks very similar to what we had before on the left-hand side, but with this subscript matrix to say we're working in a matrix model rather than in JT gravity. And this is just an integral over Hermitian matrices. This is a flat measure with some weighting that's very simple as the trace of some function of the Hamiltonian, and then insertions of essentially thermal partition functions here. So if you like, it's a statistical correlation function of partition functions when you take a random Hamiltonian with this weighting. So it's describing a special kind of ensemble of Hamiltonians. And basically due to Tufts large n counting, you get a genus expansion for this thing, which describes the genus of the Feynman diagrams you get by expanding these integrals. And the topological recursion is just a rule to get all the matrix integral results, all genus, uniquely from just the leading piece, which is the effectively the genus 0, 1 boundary, genus 0, 1 boundary, or one of these insertions. And everything else follows from that using this topological recursion. And the magical thing discovered by Saichenko and Stanford is there's a precise correspondence between this topological recursion of matrix integrals. So here's the definition of a matrix integral. It's characterized, this sort of input to define the integral is this partition function of the leading order, which is this input to the topological recursion. And then you've got these rules to get all the other higher genus and more boundaries comes from that. And these exactly correspond to the JT path integral. This leading piece comes from the disk we discussed before, this Schwarzian path integral, and the topological recursion precisely corresponds to Mirzakhani's relation. So this means we have a direct correspondence to all orders in the genus expansion, and a correspondence between this matrix integral, which we interpret as the Hamiltonian. So the matrix appearing H here, we interpret as the Hamiltonian of the quantum mechanics that's dual to this theory of JT gravity. Good. Okay, so that was a lightning review of Sachenko and Stanford. Now we get to go to the new exciting stuff. So what we're going to do is just augment this theory by including some dynamical defects. So by dynamical here, that means I can I sum over some number of defects included in the path integral, and these appear in the path integral with some amplitude lambda, which is one free parameter in my theory, and they're defined to produce some conical singularity at some location in the gravity, and I get to choose the deficit angle that is sourced by that. So this I'll take as the definition of the defect, and now I can integrate. So before we were integrating over hyperbolic surfaces, but now we have hyperbolic surfaces with these extra conical singularities in them. So my genus expansion we had before becomes a two-parameter expansion in both genus and in the number of defects. So I have this lambda to the k, which is the amplitude for defects with a symmetry factor, and then these amplitudes with n boundaries and k defects. And we could generalize later to talk about different types of defects, but here we'll just take them all to be the same. Okay. So just like we had the disk as a sort of special case before, we've got a new special case here, which is one boundary, one defect, genus 0. And so it's a path integral that looks like this. You have some conical singularity here, and it opens out to an asymptotic boundary. And this path integral was computed by Mertens and Tiriaci. So there's a different sort of Schwarzian path integral here. So for those who know about it, this the path integral for the trumpet is a hyperbolic cojoint orbit of diff S1. Here it's an elliptic cojoint orbit instead. So it's, that actually means you can get this trumpet. You can take the usual trumpet result with a boundary, the guy on the bottom left here, and set this boundary length to be imaginary. And the imaginary value is set by the strength of this defect that we have. So the defect is somehow represented by a geodesic of imaginary length. So this is just a very formal relation, but it's going to come in very useful. Okay, so this is just you can do this calculation, and this is the first result. Now for all the other terms in this expansion in genus and in number of defects, we play the same game we had before. So again, there's some geodesic we can cut on. That gives us this trumpet piece, which is precisely the same as before. And now we have hyperbolic surfaces with cone points. So there's some generalized version of the Weil-Petersen volume where there are cone points with some defects of prescribed strengths. And we have the similar formula that we had before. But now this Weil-Petersen volume has these cone points in there. There's a small caveat here, which is that we need these defects to be sufficiently strong that this outermost geodesic actually exists and doesn't encounter, you don't encounter any of these defects before you arrive at this geodesic. So that's a slight caveat that we should restrict ourselves to this range of alpha, but the results should be expected to hold more generally. But that's they're not being checked in detail for smaller values of alpha. Okay, so now we have everything we need, apart from these new Weil-Petersen volumes with cone points. So it sounds like we're going to have to work out some new technology, but fortunately, this same game that we had before, that we saw for in the calculation of the single defect disk amplitude, also works. And you can take hyperbolic surfaces with geodesic boundaries, and you analytically continue the lengths of any boundaries to correspond to defects, to imaginary values. And analytic continuation is a little bit fancy here because it turns out these volumes are actually polynomials in the length. So you just replace these b's by I alphas, and you get these generalized volumes come directly from the ordinary Weyl-Peterson volumes with just boundaries. And this was proven again for roughly the same reasons before. There's this caveat that you need sufficiently small alpha, but was proven by these mathematicians. And this also appeared recently in a different context in this paper of Kotler, Jensen, and Maloney. Okay, so this gives us everything we need to analyze the theory. We in principle have all the ingredients we need, and we just have to see what the theory tells us now. So the place to start is to ask about this, just the disk with a single boundary, a genus 0, but we now allow any number of insertions. So I'm going to start off by doing something that's analogous to this Maloney-Witten story for 3D gravity, which is just restrict myself to classical solutions and the loop corrections on top of that. So it turns out there are just two classical solutions here, which is the disk and this disk with a single defect. And the density of states looks like this. And if we take the limit of very low energies, sort of near extreme or low temperature limit, then it looks like this. And this is very reminiscent of what we saw in 3D gravity. And there's good reason for that. And this makes us think that maybe this theory is inconsistent or doesn't have a good dual if lambda is negative, because this can become negative for the same reason as before. But we can now see what happens when we add an extra defect. So let's see what happens with this 2 defect piece. So the first thing to say is this is not a classical solution. These defects tend to want to attract one another, so they like to run, reduce the distance between them. So there's actually no classical solution here, but you can nonetheless do the path integral over the configurations. And you get something that goes like this at low energies. In fact, this is the exact result. And so this we can immediately see it's down by an extra factor of lambda because we've got an extra defect, but it's also more singular at low energy. So we're seeing a sign that maybe going to this low energy regime, the expansion in number of defects and small lambda was not a good expansion, and we shouldn't worry about the negative density of states because it's in this regime where the expansion breaks down. But we can actually do much better than that. We can see what happens when we really sum over all the defects. So to do that, we need to examine what happens to these volumes at very low temperature. So low temperature corresponds to very, very long boundaries here. And it's you can use various results in the mathematics literature to get a leading order result when one of the boundaries has a very large length. And you can then just add things up with sum over the number of defects. And it turns out to be a binomial series in the energy. And so this series of corrections sums up into this shift of the square root, which means that the spectrum is supported above some energy E0, which is roughly -2 lambda here. And you can go to higher order here. This was just a leading order in temperature, but going to higher order, this turns out to work out. You can sort of start off doing it experimentally, and there's these complicated shift. It doesn't matter what the formula is here, but it can be calculated kind of explicitly, and it sort of magically works out that everything sums up into this shift of the square root. And this is a really strong constraint on what these volume polynomials look like. There's no accident here. There's a conspiracy going on. So as I said, these things are polynomials. And if you'd like to have this structure where there's a shift of the edge of the spectrum that retains this square root form, the first or all but 2 of the terms in this polynomial are uniquely fixed by what went at lower orders before. There's no choice as to what these can be. There's one term that changes the shift to next order and another term that determines sort of how the shape of the density of states changes. So it's not just a rigid shift of the spectrum. Good. So this has given us at least a sign of how we might resolve things in this 3-dimensional gravity case, and that we should include these larger numbers of Kaluza-Klein defects. Okay, but there's still more work to do. we want to understand this density of states in complete detail if we can, and we also want to understand if we still have this magical feature of a matrix model dual, which is this very rigid, very special feature of JT gravity. Is that still there? So the first step here is to really understand this leading order density of states or leading order partition function to all orders in lambda, but just at genus 0. So it turns out that this is most convenient to write in a slightly new language that is in terms of some function u of x. So this is naturally appears in the technology developed in the minimal string in around 1990 by a large number of papers that I can't list all of them, and has recently been sort of revived in the context of JT gravity by these authors. And so some of Clifford Johnson's recent papers is a good place to start learning about some of this technology if you're interested. I find useful. Good, okay, so this u of x is just some function. This is just a definition of u of x essentially, and it's equivalent to this genus 0 partition function or the genus 0 of density of states. So the function u of x defines the matrix, a matrix integral, if you have a matrix integral. So for JT, this formula defines what u is. This is I1 is a Bessel function. So there's some implicit formula, and this is what was called the string equation, or rather the genus 0 string equation in this minimal string literature in 1990. But again, for us, this is just some way of specifying what the density of states looks like at genus 0. And using this, we can just do a Laplace transform and change variables, so we get a very explicit formula for the density of states. So if you plug in this formula for JT, you'll get this famous Cinch density of states, Cinch square root energy density of states. You can go check that. And there's this threshold that appears, and the threshold is this function u of x evaluated at x equals 0. And generically, this density of states goes like a square root. So this is something we expect from matrix integrals, this feature that we saw. Okay, so what happens when we add these defects? So using this technology and some of the minimal string literature, Mertens and Turiachi very recently gave an explicit closed form expression for the Weil-Petersen volumes at genus 0 with n boundaries, which looks something like this. Again, the detailed form is not terribly important, apart from the thing that goes in is this u of x for JT gravity, and it's got an explicit formula. Now we can just analytically continue some of these lengths and get now an explicit formula for that looks something like this for the, again, genus 0, one boundary, k defect volumes, which is what we need for our disk density of states. And it turns out that you can just plug this formula in to our expansion for these volumes and do the sum explicitly. So this turns out to use something called the Lagrange reversion theorem. Here it is on Wikipedia. It's got a nice explanation of how it works and a little proof there. So it's very clear. But from Wikipedia, you can see already that there's this thing here that looks, it's roughly speaking, is the string equation. It's an implicit definition of a function, and then a sum over some powers of things with derivatives, which looks sort of like what's going on here. So it gives you some very brief flavor of how this sum goes, but I don't want to get into the technical details. But it's quite fun going through and seeing how it all works out. But the upshot, when you get everywhere, when you do this sum and work out the new density of states, and is that you can be summarized as a linear deformation of this string equation. So we had this definition before where there's an implicit equation here. You solve this implicit equation and you plug it in this sort of Laplace transform, and it gives you the partition function to genus 0. All we've done is we've deformed that string equation, and in a very simple way. And it's obvious now what you can do is add multiple types of defects with different amplitudes for including them, different defect angles, and they just all add in this linear way in the string equation. Okay, so this is the genus 0. Yeah, so I should just briefly mention where all the nonlinearities come from here. So this disk density of states had an expansion that had new terms at every order in lambda. but X here, this new string equation, was just changed to linear order. But all the nonlinearities come in from this shift in the edge of the integration region. So E0 is some complicated nonlinear function of lambda. Okay, so this gives us a genus zero density of states. Now we'd like to know if this is a matrix integral. And perhaps, so I can talk a little about 3D gravity at the end. I won't go through the details. I'll just give you the upshot. And the answer is yes. Quite magically, it works out that so all orders in the genus expansion for any defect parameters, you really obey this topological recursion still. So there's a defamation theorem of Einard-Norren.
5 minutes.
Thank you. Good. Yeah. So yeah, you can go and read the paper for details, but it turns out that any number of boundaries and any genus matches the expectations from a matrix integral. So we still have this structure. Okay. The last couple of things to say about, or the very last thing to say about this theory of JT with defects is there's another way to think about the theory, which you can redefine the defect insertion just by saying that there was going to be a conical defect in the metric with some amplitude, but you can define it in terms of the action by inserting some exponential piece. And why that gives you a defect, because phi appears in the exponential here, it combines with the Lagrange multiplier that fixed the curvature to be constant. So effectively the action gets deformed by a delta function at the location of the defect with this linear dilaton. And that means that the curvature has this delta function, which gives you a conical singularity. So an insertion in the path integral is equivalent to what we were saying before. Up to some subtleties, we have to define the measure here and say what happens when these things are coincident, which amounts to regulating the theory. But at least there's some definition that looks like that. And now we can sum over these insertions. So we can include k insertions, and there's some symmetry factors, and the amplitude is lambda. And this sum just exponentiates. This is familiar from sort of instanton gas techniques, for example. And all it does in the end is deforms the potential. So this u of phi equals 2 phi gives you JT. And now we get new exponential terms in the potential. So this gives you a new family of dilaton gravity theories where we have a matrix integral dual. So we can describe it in terms of this new potential. Okay, so just a brief summary of what we've learned is that this feature of JT gravity, that there's a matrix integral dual and you can do the path integral exactly, has this generalization with many parameter generalization. And we can really understand things. Okay, so in the last couple of minutes, fortunately, I don't have too much to say about 3D gravity because it almost all follows immediately from just applying what we just learned in 2D gravity. So here's the proposal. We already saw at the beginning that to describe near extremal BTZ black holes, we can get a good approximation to the physics by going to this two-dimensional theory. But now we should include these Kaluza-Klein instantons, which are a version of these defects. This was what the answer looked like if we just included classical solutions. But now we should sum over any number of Kaluza-Klein instantons. So that means including these sort of off-shell contributions to the path integral. And this negativity that was pointed out gets resolved in this beautiful way into a new shift of the extremality bound by this non-perturbatively small amount that depends on the spin. And so these configurations with multiple KK instantons in 2 dimensions, these multiple defect instantons, are smooth 3-dimensional manifolds that are called Seifert manifolds. Good. And I should briefly mention that this a sort of sum of contributions that give a shift of the extremality bound is not something completely new, but there's a perturbative version of this that you can actually see from the conformal bootstrap, which sort of inspired this the hunt for these kind of contributions. Good. So this just leaves me to speculate about what this might mean for 3-dimensional gravity. We've certainly revived the hope that there may be a pure theory that we can hope to understand. But what does that theory look like? It comes with a bit of baggage. So in particular, we have these contributions in the path integral, which I'll call space-time wormholes, where we have several disconnected Euclidean boundaries. So in JT, there were these multiple circles, And in 3 dimensions, we might have multiple disconnected torus boundaries. And these are all joined together dynamically by the gravitational path integral. And that in JT gave rise to an ensemble dual. So the question now is whether the same thing should apply to pure 3D gravity. So there was some recent work on this. In particular, I'll highlight this paper of a couple of weeks ago of Kotler and Jensen. So they did a very detailed calculation of one topology, which is the torus times an interval with 2 torus boundaries. That certainly gives some evidence for what this ensemble might look like. And there's a slightly different ensemble of free theories was talked about in these 2 papers recently. So we saw what this looked like near extremality, and it looks like it's got the structure of a matrix integral, which is a very natural type of ensemble to pick a Hamiltonian from. But that can't be the whole story in 3 dimensions. There's more structure here. You can't just have a matrix integral, an independent matrix integral for every spin, for example, because these things need to be tied together by the fact that there's local interactions in space. So for example, there's modular invariance will tie together the matrices in different spin sectors. And there's also more structure from the fact that there are correlation functions and so forth. So understanding what kind of ensemble there might be. And this is in particular very hard for CFT. We don't expect there to be a sort of continuous moduli space of chaotic CFTs, but rather we expect them to be isolated points in some moduli space that it's very hard to see how you can have some ensemble. So that deserves better understanding. And just some philosophical comments to wrap up is these are very closely related, these space-time wormholes are very closely related to the recent discussions of the page curve. I'm sure we'll hear more about that later this week. These replicable wormholes are examples of this that we will learn about more. And also a connection to sort of cosmology or physics of closed universes, which goes back to work in the 80s of Coleman and Giddings and Strominger and others. And in the context of page curve and so forth, we with Don Rolf recently revived this idea. So there's very good reasons to understand how this web of ideas connects. And in general, it gives us a new paradigm or possible way to think about semi-classical gravity as giving us some sort of statistical description of chaotic theories that I think there's a lot more for us to learn from. So with that, I'll thank you for your attention and invite questions both on the Slack channel over the next few days and right now. So thanks.
Thank you very much for an excellent presentation. I see a question here. Upamanyu Moitra, could you please ask your question?
Thank you. This is probably a very naive question, and I apologize if you have already answered it in the talk. But I was wondering why you do not sum over all possible value of the defect parameter alphas when you find the connected correlators, which is only a function of the renormalized boundary lengths.
Yeah, so we're taking as part of the definition of these defects as a fixed value of alpha, and it's really analogous to some Lagrangian parameter. So in fact, in this expression where we insert a defect with a piece of the action like this, alpha is just a Lagrangian parameter that we can fix. And in the 3 dimensions, we again saw that alpha has to be some specified value. There it was, alpha has to be a half, for example, or 1 over some integer. And you don't have the chance to you don't want to integrate over continuous values. So we have this possibility to include multiple defects with different values of alpha, and you could generalize that to an integral here, which would be like a measure for alpha as well. So you would have the opportunity to do that. The important point is that when we define the theory, we can choose what we want to do. That's part of the definition of the theory.
So in the putative 1D dual theory, the defect parameter should also appear as a parameter in addition to the renormalized lengths, right?
Yes. So the thing that defines this theory is the string equation. This is what defines the dual, and in this genus zero density of states, or this leading order piece. So it's this disk genus zero density of states that determines everything else, and this function appears in that density of states. So that's how the alpha dependence comes about.
Thank you very much.
There's a question from Andrew Strominger. Please go ahead.
Yes. So are you saying that pure 3D gravity doesn't have an ordinary partition function, that there's only an ensemble average? Is it a quantum theory without an ordinary partition function, or how are we supposed to think about that?
At the moment, it's really speculation. We have a certain limited set of contributions to the path integral that we can study in some limited regimes, and really the speculation is based on possibly an unwarranted extrapolation from the two-dimensional examples. But it's certainly a logical possibility that if you compute the partition function defined by a one boundary path integral, it gives you something with for example, with a continuous density of states that is just not consistent with a single unitary dual. So this continuous density of states, again, is what you see in JT gravity, for example.
Well, I could ask similar questions about JT gravity too. I guess you've related them in a nice way. But so do you or don't you think that 3D gravity, pure 3D gravity, exists as a quantum theory of gravity, quantum mechanical theory of gravity in 3 dimensions? Or are you saying that only the ensemble averages exist?
So from the three-dimensional point of view, so this was one of the points that we tried to make in this paper with Don. From the three-dimensional point of view, there's really, and again, this goes back to this old work, there's really nothing wrong with this having an ensemble dual from a quantum mechanics point of view. It just tells you that there's a non-trivial Hilbert space of closed universes that are playing some role. So the fact that we have these strange features from the dual, there's some ensemble, which we could talk about as super selection sectors if you like, is related to some unobserved state of closed universes that we can't directly access. And so there's a perfectly consistent quantum mechanics, it's just it has super selection sectors. So it's, yeah, so whether you call that consistent or, okay, there's a question of language, but there's a perfectly consistent quantum mechanics.
Well, I would say there's a consistent quantum theory in every super selection sector.
Okay, yeah, this is
Okay, there's another question from Nathan Benjamin. Do you want to go ahead?
Hi, Henry, it's a really nice talk. Can I ask how your result is consistent with modular invariance from the 2D CFT? In particular, yeah, go ahead.
Carry on.
Yeah, for example, can you write down a spectrum of a C bigger than 1 theory with a twist gap bigger than, C minus 1 over 32? That's positive everywhere in modular invariance?
So far, I don't know how to explicitly give you a concrete spectrum like that, but we can at least understand how we evade the arguments that you and friends gave. And the crucial point is that the new corrections here are, so the sort of third term, if you like, that we're adding is something that grows slower with spin, but it's more singular close to the edge of BTZ. So if you do a modular transform of that, it's something that, because it actually is e to the 0, so it doesn't grow with spin. And in the modular transform dual, that tells you that it has dimension C minus 1 over 24 or something. It's at the black hole threshold. But the modular transform of something that's more singular at low energy is something that grows polynomially with spin. So the important thing is that we have to add some infinite set of operators, but it's infinite in some very mild way. It only grows polynomially. We have a follow-up paper that is in preparation that I hope will satisfy you more. And I can give a more complete answer in the future.
Thank you. There's another question now from Alejandra Castro. Please go ahead.
Hi, hello. You can hear me, Henry?
Yeah.
Okay. So I was curious about what would this tell us about SL2 Chern-Simons theory. So from that point of view, I could imagine that if I quantize Chern-Simons theory, there will also be solutions that won't have a nice classical interpretation. But I don't know if I would conclude that I will have an ensemble theory if I quantize SL2 Chern-Simons. So I don't know if you have any comments about what this tells us about Chern-Simons theory and its connection to 3D gravity.
Yeah, so one of the things I'll perhaps highlight is that in this paper of Kotler and Jensen, the differences between Chern-Simons theory and 3D gravity showed up in quite an important way. And there's some global differences and differences in the measure that were rather important. But to directly to your question, the ensemble here really comes not from the fact we're including off-shell solutions per se. It comes from the fact that we are including contributions that are that connect multiple boundaries together. And once you include those contributions, if you want to have the boundaries become uncorrelated, you need some miraculous cancellations to happen. And that could happen, but there's certainly no obvious way for it to happen. I'm not sure if that gets at what you're asking.
Okay, Sandeep Trivedi.
Hi, Henry. Thanks for a nice talk. I want to slightly follow up on what Andy was asking, because I'm also a little confused about this. As far as I know, by appealing to super selection sectors, you can't explain the JT gravity partition function as coming from a unitary theory. Is that right? How then is it supposed to work in 3D gravity? I thought you were suggesting that it could work there.
So there is a way of describing the JT gravity in terms of superselection sectors, which is simply that we have well, there's a matrix integral. Perhaps we don't need a formula, but yeah, something like this. So JT gravity is, so we have something that if H was some unique Hamiltonian, this would be the partition function, and we would have just n disconnected copies of the partition function. So really the Hamiltonians label the superselection sectors. So you can think of the integral over Hamiltonians as a sum over superselection sectors, or in the language of a paper with Don, the H actually labels, the Hamiltonians label states of closed universes. So there is a way to describe this in terms of superselection sectors. Once you're in a superselection sector, that is to say you have a definite Hamiltonian, then all these traces just factorize and you're left with just the usual partition function in a single unitary Hamiltonian.
Okay, last one.
Okay,
Go ahead.
I see. No, I was just saying, so you're just saying what one was thinking of as a sum over the different random Hamiltonians, you say you just want to think about as a sum over different superselection sectors. And that's presumably consistent with, then, usually you get locality, etc. in superselection sectors. And I'm not sure how to phrase it here, but there's probably some story like that as a consistency check of that picture.
Yeah, so okay, in JT gravity, there is the Hamiltonians, you're integrating over every possible Hamiltonian. So that means that once you're in a superselection sector, generically it'll look like a chaotic Hamiltonian, but there's no locality there. So these Hamiltonians can be as wild as you like. There's no way to write them, for example, as k-local Hamiltonians or something. So if you want to have some other notion of locality in your theory, so for example, an SYK Hamiltonian can be written in terms of fewer variables than a generic Hamiltonian. So if you want to have some extra structure, some locality, then you need to integrate over some smaller set of matrices. And that's the sort of feature I was alluding to that needs to be there for 3D gravity. And we need to understand, if we are to have some kind of ensemble, we need to understand where these kind of locality constraints come from, because that will mean we're integrating not over all Hamiltonians, but over only those Hamiltonians that can be written in some local way, spatially local way, for example.
I see.
There's a question on the chat, which is related, I believe, to what you just said. If JT does not have a well-defined partition function formulation, only as an ensemble, how can I know that the path integral over the modular space of bordered Riemann surfaces satisfy unitarity? I don't know if you want to add anything, Henry.
Let's see. Yeah, so I think this relates to somewhat again this perspective of baby universes. Is there is a unitary theory, but you have to include in that theory not just the state of universes with asymptotic ADS boundaries, but also the state of closed universes. And the fact that you have some unknown state of closed universes is what causes these superselection sectors and sort of apparent loss of unitarity.
Okay. All right, last question, Mukund Rangamani, please go ahead.
Hi, Henry. I was wondering if the following is a good toy model of what's going on. If you took a quantum field theory at finite temperature and finite angular potentials, you would get a good partition function, a good grand canonical partition function. Now, if you actually want to extract from it the density of states at finite energies and finite angular and finite angular momenta, you would want to do some kind of saddle point evaluation of the grand canonical partition function back to the microcanonical ensemble. And this is subtle, and in general, the saddle point that you would use for the canonical transformation, just a beta Laplace transform, is not the same saddle point. There's a shift in the saddle because of the angular fugacities. And gravity a priori seems to prefer fixing angular velocities, not angular momenta. Is the picture that you have sort of elaborate version of the same statement?
I'm not sure I have much to say on the specific, but on the general philosophy, this is certainly an alternative point of view, that instead of having at heart a statistical ensemble of theories, that instead gravity is giving us some other kind of statistical description from another kind of coarse graining than perhaps something that's only valid in an expansion at large central charge or something like this. And this is the sort of perspective I think that that was given in this paper of Bellin and de Boer and some other work by folks at UBC that want to understand this as having a statistical origin, but in the sense of ETH, statistics within a single theory rather than statistics in multiple theories. And that's certainly a live possibility as well. That's something worth exploring.
Okay.
Okay, thanks very much, Henry. Let's thank you again for an excellent presentation, as well as very interesting. So I think we should break for 5 minutes, and we will restart for the second plenary talk of the second session at 6:05. So that's 6:05 South African time. I think that's 12:05 East Coast time in the States. So let's have a 5-minute break, comfort break. We'll see you in 5 minutes. Thank you. Henry, maybe you want to, yeah, thanks. Thanks very much.
Stop share. Thanks for hosting the session.
Thanks, Henry. That was a great talk.
Sure.